Thank you, Flora. Thank you very much for the invitation. It's great to be able to give a talk here. So I'm going to talk about the joint work with Thomas Gemünten, who is, well, no, actually, he was my student, graduated last summer. And then this is also based on previous work with two physicists, Alexandre Belin and Alex Maloney. And I should say I'm a sort of half physicist, half theoretical physicist, and half mathematician. So actually, I figured probably the most useful type of talk I could give here is give some idea of what types of questions that people on the physics side are interested in, and hoping to inspire people to maybe think about things in a slightly different way, which may be more amenable for physicists to understand. I should also say that I'm going to present results which have been published, but sort of in a larger picture of this idea of holographic families and large central charge limits and so on is very much under construction. So some of the things we've done are correct, but most likely we did not do them in the most elegant way, in the most general way. So Thomas and I at the moment are, in a sense, in the process of redoing some of the things that we're going to present in a more elegant and more general way. So in particular, I will probably not spend too much time going into technical details of proofs and so on, but rather try to convey the overall picture, the overall message of what we're interested in. So holographic families of vertex operator algebras. So what do we want to do? Well, we want to consider families, or if you want, sequences of vertex operator algebras. So we have something like Vn, or I guess, strictly speaking, I should really give the full tuple something like the space Vn and the state field map Yn, the conformal vector omega n, I guess the vacuum and so on. But for convenience, I will often just write Vn. And n is the index of this sequence or family of vertex operator algebras, and we're just taking it to be natural numbers. And we want these families to have certain properties. So in particular, what we want their central charge to go to infinity, in the sense that if the central charge of the nth member of the sequence is Cn, then we want this to go to infinity as n goes to infinity. And actually, most of the time, what we're going to do is there's going to be a very simple expression of what the nth central charge is. It's not really necessary, but I think for all the examples I'm presenting today, it's going to be the case. It's simply going to be linear. The nth central charge is going to be linear in n. So it's something like C1, the central charge of the first term in the sequence, times n. And so a large part of what a holographic family is, what defines a holographic family of vertex operator algebras, is to deal with a large n limit, or equivalently a large central charge limit. What else do we want? We want those Vn's to be of CFT type. At least for the second part of this talk, this is going to be crucial. So what that simply means is that V0, if we write down the, if we write down the underlying vector space V, then this underlying vector space is of the form V0 plus only positive weights, so V ends with n bigger or equal to 0, and V0 is spanned by the vacuum. So I'll use this physicist type ket notation to denote the vacuum. So V0 is one-dimensional spanned by the vacuum. The other thing we want to assume, and this is really just an assumption for convenience, I think pretty much everything I'm going to say would also work without this assumption. But for convenience, we want to assume that those Vn's are unitary. And the reason this is convenient is we often want to work with a orthonormal basis. Let's call it capital phi. So this is going to be a homogeneous homogeneous orthonormal basis. And as we'll also see in just a second, sometimes it just makes life easier if you can talk about the norm of a vector or the norm of a state of this vertex operator algebra. And then finally, for a start, at least in the beginning, let's also assume that these Vn, assume that they are holomorphic. So at some point during the talk, I will relax this assumption, namely when you start talking about the orbifolds and fixed point algebras and so on. But for a start, let's assume that they are holomorphic. And in a sense, in the end of the day, the goal really would be to, even if we have to work with something non-holomorphic on the way, in the end of the day, we would really want to say something about holomorphic. But as we'll see, we're not quite there yet. So we'll have to relax that assumption a little bit. So what's the point from a physicist's point of view of considering these types of families? Well, what physicists would like to do is they would like to define a large end limit or a large central charge limit of this family. So we want to introduce or define some notion of a large N, or as I mentioned, equivalently, a large central charge limit. So sort of in a very sketchy notation, roughly speaking, what we want is we want something, if we have this family of Vn's, and if we send n to infinity, we're hoping that this will converge to some object. Let's denote it by V infinity. And this object, we're hoping will have some interesting algebraic structure. Actually, as it turns out, what we can usually hope for is that this limit V infinity is no longer going to be a vertex operator algebra, but it's still going to be a vertex algebra. So essentially what's going to happen is, for reasons that are actually pretty straightforward, basically because the central charge goes to infinity, it means we're sort of throwing out the structure of the Virasoro algebra. So that's why it's no longer a vertex operator algebra. So in a sense, the goal is to establish a framework for these types of large end limits. And then once we feel comfortable with this framework, to actually construct examples of such theories. And maybe to just give you a sort of more of an idea of what we expect to happen, or what we want to happen, what we want to happen in this definition of a large end limit, let me start out with an example. And namely, let me start out with extremal vertex operator algebras. So maybe as a very quick definition first, and this is again inspired by physics, let's define a subspace of V, of a vertex operator algebra V, which we'll call the light part, or maybe the light spectrum, or the light states of the theory. And basically it's simply, let's assume again it's a CFD type, but basically what it is, you're only keeping the homogeneous subspaces with weight 0 up to C over 24 rounded down. So this is, I'll call this VL, and it's basically the light states of V. And we can use this definition to define what we mean by an extremal vertex operator algebra. So an extremal vertex operator algebra is a holomorphic VOA V such that all the light states, all the light part of the vertex operator algebra is completely given by just a vacuum and its Virasoro descendants. So, you know, just a basis would be something like the vacuum, and then we have, of course, the Bezoar element itself, and then you have L-3 acting on the vacuum, etc., etc. So an example of such a extremal vertex operator algebra is the Monster Voa. So V natural is indeed the Frank-Lipowski-Merman construction is indeed an extremal VOA. For n, I guess I haven't really defined n, so let's instead say for C equals 24. And probably the easiest way to see that is simply, you know, write down the character of the V of V natural. And so what we get is we do indeed get q to the -1 plus 0 plus 196,884 q plus ... And basically, the first two terms in this case for C equals 24, as you can see, the first two terms are the terms corresponding to the light part of the spectrum. And indeed, we have a vacuum here, and then we have nothing of weight 1. And then at weight 2, we have, of course, the conformal vector, but then we also have a very large number, 196,883 new additional basis elements in V2. And in a sense, this may give you a hint of why we're having this definition of an extremal VOA. The point is because we are insisting on having a holomorphic vertex operator algebra. The character, of course, has to be modular invariant. But basically, what this extremal VOA definition tells you is that you're allowed to fix all the coefficients of this character, which modular invariance allows you to fix. So in particular, in this case, you're allowed to fix the q to the -1 term and the 0 term. But then once you fix that, you have no choice to change the remaining numbers in the expansion of the character. For those of you who know about extremal lattices, this is kind of a very similar story. If time permits, I will briefly return to extremal lattices. So the motivation for the definition is in a sense the same. Maybe I should actually here give the names of the people who actually proposed this. It was initially proposed by Gerald Höhn, but then also Edward Witten on the physics side did some work on it, and especially in particular connected it to the physics, to a question in physics having to do with holography. The slight difference between extremal lattices and extremal vertex operator algebras, and maybe I shouldn't call it a slight difference because it may actually make all the difference, is that as is known from work from Mallows and friends, that extremal lattices, they don't exist for arbitrary dimensions, so there's no infinite family of extremal lattices. But basically what goes wrong is simply that if you try to write down their data function, you get negative coefficients. For these extremal vertex operator algebras, that doesn't happen. So at least you can write down characters which look like that they could come from a perfectly healthy holomorphic vertex operator algebra, and you can write down an infinite family of such characters. And because you can do that, unlike for extremal lattices, people have actually conjectured that there is a infinite family of such extremal VOAs. So more precisely, the conjecture is that for all C being a multiple of 24, so we want to concentrate on central charge being multiple of 24. There exists a unique extremal VOA. Now, this is a conjecture, but the status of this conjecture is very much open. I think different people have different views. Personally, I'm somewhat skeptical that there really is such an infinite family of extremal VOAs. But still, just for argument's sake, let's assume that there is such a family, just as to give an example, because in a sense, if such a family will exist, it would be the simplest example of such a holographic families of vertex operator algebras, which does have a large end limit. So, I'll just assume they exist. It doesn't really matter if they don't. Actually, as you may realize, it's not really necessary for what I'm going to do, even for this specific example. But it makes, if they existed, it would make life slightly neater and nicer. So for argument's sake, let's assume this is true. And if this is true, then they do have a large n limit. So these extremal VOAs, so I'll just use the abbreviation EVOAs, extremal VOA. These VOA have, if they do exist, indeed, they have a large n limit. Let's denote it by V infinity. And basically what happens is that on the one hand, as a graded vector space, what happens is simply that V infinity is going to be the Virasoro vacuum module. Or maybe slightly more precisely, it's going to be the Virasoro vacuum module when C is bigger than 1. So the only singular vector would be L-1 acting on the vacuum. And I should say, if I draw this, this is supposed to be some squiggly line here. This squiggly line here means it's isomorphic as a homogeneous vector space. So it's definitely not isomorphic as a vertex operator algebra. But basically what this simply means is that, you know, the dimensions of the homogeneous components of the vector space are the same. So another way of phrasing it, and maybe slightly more concrete way of phrasing it, is that we can write down the character of this large n limit of these extremal VOAs, and it's simply given essentially by the eta functions times 1 minus q. Actually, I should put some quotation marks here. I guess what I really mean by the character here is we multiply the standard definition of a character by q to the c over 24, just to make sure that otherwise you'd have a q to the minus c24 term everywhere, which would of course the exponent would go to minus infinity, and we don't want that. So it's just a slightly shifting of the definition of the character. And then we can do something more. So we're the basic idea is that essentially the whole algebraic structure that we're seeing is going to come from almost a conformal vector. But it's only going to be almost a conformal vector because we want to rescale, we want to redefine the conformal vector slightly. And the way we want to do is we want to define something which I'll call omega tilde for every n. And we want to define it as 1 over the square root of n times the actual conformal vector omega n. And the reason we're doing is it ensures that the norm, and remember we're assuming here that it's a unitary theory, so we're using the norm here. So what it ensures is that the norm, or if you want the norm square, which I'm going to denote in, again, sort of this physicist bracket notation, but this is simply the norm squared of this omega tilde n, is going to be, and I hope I didn't screw up the computation, but I may be off by a constant, so please correct me if I'm wrong. But the point is, if we compute this norm here, then what we find is that there is, of course, because of the central charge of this nth vertex operator algebra is 24 times n. And this 1 over square root n, we introduce it in such a way to cancel out the n dependence, and then I think we do get 12. So the point is, if we take the large n limit of the norm of the omega tilde n's, then we do end up with something finite, which wouldn't have happened if we hadn't rescaled. And then a sort of the analogous thing that we can do is we can also talk about computational relations, that is the algebraic structure. And let's do this. Let's compute the commutator of L tilde n and L tilde m. And again, L tilde simply is the rescaled, I mean, it's the modes that come from this rescaled definition of the conformal vector. And the point is that because of this 1 over square root of n rescaling, what happens is that in the Virasoro algebra, the term proportional to the central charge now, which would contain an n, this n again is cancelled out by this 1 over square root of n. And then, of course, we have the second term in the Virasoro algebra. But now, because of the rescaling, what happens to this term is that it picks up a factor of 1 over square root of n. Then we have the L tilde plus n. And so basically what happens is that now, if we look at this computational relation here, there is a notion, it makes sense to try to send n to infinity. And basically what happens is over here, this term here is of order 1 over square root of n. So in particular, it would just vanish. It would go to 0 as we send n to infinity. Whereas this term here is of order 1, which means it's simply going to be 2m times m squared minus 1 delta m plus n 0 times the identity. So sort of in a very rough way, and I'll make this more precise in just a minute, this is what a large n limit would look like. It's going to be a vertex algebra based on this space V infinity, and it's generated by the limit of omega tilde, and the algebra that the modes of this omega tilde satisfy are of this relatively simple form. So the second term coming from the Virasoro algebra drops out because we're taking n to infinity, and only this first term survives. And then in particular, and this is maybe a slightly more physicist perspective, for instance, as a physicist, what you might be interested in is computing correlation functions or matrix elements. So what do I mean by a correlation function? Well, it's the function whose power series, whose appropriate Laurent series expansion in, say, the variables z and w agrees with the formal series that you get if you compute, for instance, this formal series of the matrix element here. And then what would happen, and again, I may be slightly wrong in the normalizations or so, but roughly speaking, what happens if we do this computation here, and I should really put all the n's here, what we find is that we can again expand the resulting function. If we do it for general n, we can expand it in a 1 over n or 1 over square root n expansion. So we get something like, I think it's like 12 square over c minus w to the 4 plus 12 square over z to the 4 plus 12 square over w to the 4 plus additional terms, but these terms would again go like 1 over square root of n. So in a sense, what physicists are after is, these types of physical quantities like correlation functions and matrix elements. What they would want to do is to have a 1 over n expansion. So have a systematic way of, for instance, computing the leading term, the order 1 term, which is just these 3 terms here, but then potentially also a systematic way of computing the subleading corrections. And in a sense, to make the connection to something which you've maybe seen if you've worked on quantization, in a sense, you can think of, at least conceptually, you can think of 1 over n as playing the role that the Planck constant h bar usually plays in quantization. So conceptually, what happens is that if you're trying to quantize a system, what you're computing is some sort of h bar expansion as h bar goes to 0. And what we're doing here is somewhat similar, but the role of this constant, the Planck constant h bar, in which we usually expand, is being played by 1 over n or maybe 1 over square root n. And physically, what happens is, in a sense, exactly some sort of quantization. So the idea is that we are trying to quantize gravity secretly. I'm not going to say too much about it, but that's basically what happens. So we're trying to quantize gravity, and sort of the large n limit, the leading term would be a classical result, classical gravity, so something you might be able to compute using general relativity. And then the corrections, say the 1 over square root n terms, would give you quantum corrections. So those would be the quantum contributions to the original classical result. So that's kind of why physicists are interested in this type of limit. Okay, so the point now is, of course, that I've just simply said I assume that these extremal vertex operator algebras exist, and then if they exist, they actually do have these nice properties. We can define a large n limit and so on. But the point, of course, is we do not know it. We do not know if those extremal vertex operator algebras exist. So in a sense, the goal of the rest of the talk is to find other constructions of vertex operator algebras that actually do exist, where we know they exist and we can construct them, and then try to see if they, even though they're not extremal VOAs, if they still have a large central charge limit, and also to see how close we can get to extremal vertex operator algebras. So let me just point out two features of extremal vertex operator algebras. The second feature actually already talked about quite a bit, but let me also talk about the first feature a little bit. Extremal vertex operator algebras have what I would call few light states. And whenever I say state, I mean, maybe I should, this is really terminology from physics, but basically it just means vectors in the in V. So few light states simply means that the dimension of the Vn's are very small for the light part of the vertex operator algebra. So in particular, an extremal vertex operator algebra has exactly been constructed in such a way that the dimensions of VL, the dimensions of the light part of the vertex operator algebra, are as small as they can possibly be, because they need to accommodate the Virasoro algebra. But the definition of an extremal VOA is there's nothing more than that. So few light states, simply meaning that the dimensions that show up in VL are minimal. So the goal will be, or part of the goal of what we're trying to do is we'll try to construct families of vertex operator algebras which also have few light states. And we'll actually try to see how close we can get to these extremal VOAs to a theory which has a vertex operator or a family of vertex operator algebras which has minimal spectrum, that is minimal dimensions of VL. And then the second feature, and this I already talked about a little bit. So these extremal VOAs have, if they exist, they have a large N limit. More precisely, what that means is, so the features that we have, which allow us to say that there is such a limit, is first of all, the dimensions of the Vn's all converge. That is, the dimension Vn for fixed n converges to some finite number. So maybe I should say pointwise in the sense that that is, if we fix the weight, that is the little n for the, we're fixing the homogeneous component, then as we send n to infinity for these extremal vertex operator algebra, they converge. And I mean, they converge actually in a very rapid way, simply if as soon as little n is smaller than c over 24, or I guess in this case smaller than capital N, the dimension will simply be fixed and will be given by the dimension that we can read off, for instance, from this character here. The point of this is, of course, because we have something like they converge to some number, then what we can simply do is you can define the dimension of the homogeneous component of V infinity to be the dimension, to be this limit for fixed little n. Now, the second thing we did is, in order to talk about this large n limit, is we needed to identify sequences of vectors in this family. So we wanted to identify sequences an in the Vn's. And then what we actually, the way we did it for extremal vertex operator algebras is we wanted to do it in such a way that the structure constants converge. So if we define or we identify three sequences, say AN, BN, CN, and then we compute the structure constant. I'll give the definition of the structure constant in just a second in case we need it. Then if what we wanted to happen is that the structure constant converge to something. So we wanted to have something like FAN, BN, CN, N converge to something. And what we're going to do is we're going to take this to be the structure constant of the limit vertex algebra of the theory. So the structure constants are simply given by this inner product here. So it's acting with a B mode on a C vector, and then we get take the inner product with A. So there's a bunch of weights in here. I hope I'm getting them right. And it simply turns out it's convenient in this large n limit story to work with the structure constants. And then the idea is that we can recover, if we prefer to talk about the state field map in the limit vertex algebra, we can simply recover it in the usual way. So the state field map B acting on the vector C is simply given by a finite sum. So here we want to sum over the basis that we have. So this capital I is a basis, but this will turn out to be a finite sum. And then again, there's a bunch of things in the exponents, but it's not terribly important. But the point is that if we have these FABCs, then we can recover the state field map. And basically what happened up here is, if we look at this, at the definition of the commutator of the L tildes, roughly speaking, this thing here is something like the structure constant of F W tilde with the vacuum. And this thing here is something like the structure constant of W tilde. And this structure constant, W tilde goes to 0. And so it indeed converges, it converges to 0. And the structure constant W tilde vacuum also converges to something like 12 probably, or some such number. Okay, so if we want to try to find, if we want to construct such holographic families of vertex operator algebras, what we want to do is we want to make sure that those two properties hold. So on the one hand, we want to make sure, if we want to make sure that there are few light states in the theory, in the vertex operator algebra. And then on the other hand, we also want to be able to define a large n limit. And for this large n limit to have any chance of existing, we need to make sure that those two properties are satisfied. So we need to be the dimensions of the homogeneous components of the VNs need to converge. And then secondly, we need to be able to find such sequences which have structure constant that converge to something. So these are the two things that we're aiming for. And so the question for the remaining time, 15 or 20 minutes of this talk is, can we find holographic families that actually exist? So we don't want to assume that extremal vertex operator algebras exist. So instead, we want to actually construct explicit examples which do have such a large n limit. Okay, so let's just get started with a possible construction and see if it works. And it will actually fail, but the way it fails, it will give us an idea of what we can do instead. So let V be a holomorphic VOA. And actually, we also want it also, let's also take it to be unitary. And let's take it to be of CFD type. Now, what kind of family could we define? Well, we want to have some sort of large, we want the central charge to go to infinity as you descend n to infinity. So a natural thing that we can try to do is we can define Vn simply to be the n-fold tensor product of this VOA V. So the central charge of the nth member of this family or sequence is simply going to be the original central charge multiplied by n. But this is actually an example which fails immediately. One way to think about why it fails is the problem is that Vn has a lot of light states. So this has many light states. Well, what do I mean by that? It's not a mathematically very precise statement, but what happens is, for instance, if we simply look at the dimension of V2 and say in the nth member of this family, then this, no matter what we do, the dimension of this is going to be at least as large as n, simply because there's n different ways of having the original conformal vector distributed over those n factors. In general, there's going to be many, many more states actually. And as you go higher and higher, it will get worse and worse. For V4, you have at least probably like n square, etc., etc. So this is very bad. So if we try to send n to infinity of this tensor product VOA, the dimensions are simply going to diverge. So it doesn't really make sense to try to impose a large end limit on this. So what we need to do is somehow we need to eliminate a lot of those states. So we want to make sure we want to eliminate so many of them that in the end of the day, as n goes to infinity, we're only keeping finitely many of them, because then if that happens, we have a chance of having a large end limit. So what we want to do is we want to reduce the number of states. So you want to make that dimension smaller. And the way we want to do it is we want to orbifold. And more precisely, we want to orbifold by the symmetric group. And the observation is simply that the symmetric group is definitely a subgroup of the automorphisms of this tensor theory. And how does this work? Well, the symmetric group simply acts by permuting the factors. So we have n factors, and of course you can permute them, and it's straightforward to check that this is an automorphism of this vertex operator algebra. So this Sn acts by permuting factors. And now when I say orbifolding, there's in a sense two things we can do. One of them is easier, and that's actually the one thing we're going to do. The other one is a bit harder, and that's the thing we're aiming for, but we're not quite there yet. The first thing we can do is we can simply consider the fixed point algebra, subalgebra of the vertex operator algebra. So if you have Vn, then simply what we do is we're keeping all the subspace of this tensor product vertex operator algebra, which is invariant on the permuting factors. And this is indeed what we're going to work with. There's a big drawback of that. Even though we started out with something which is holomorphic, so V is holomorphic, and Vn, that is the tensor product, is also holomorphic, therefore. The point is, of course, that now that we're considering the fixed point subalgebra, this is no longer holomorphic. So, it's still fine to work with it as a vertex operator algebra, but really what we wanted to do is optimally what we would like to do is work with a holomorphic VOA. And so what we should really do is we should try to find a holomorphic extension of this thing, to find holomorphic extension. So something like, I'll call it V orb, and this would just simply be the fixed point algebra, subalgebra, but then we would add basically a bunch of modules coming from the twisted modules in such a way that if we adjoin them to the fixed point algebra, we recover something holomorphic. And ultimately, this point number 2 is what we would really like to do. But today, I will only talk about some results. I will only talk about results for number 1 here. And I can briefly talk about what we expect for this more complicated case number 2. From a physics side, it's assumed that it will work just the same, and there's some rough arguments why it could be, but it's definitely more subtle and there's more work needed there. So let's do number 1 for a start. Let me write down a theorem that we had in Thomas and I had in a paper. So the theorem is a paper. I should say that it relies, it's based on previous work, the other previous work I mentioned at the beginning. So this is based on previous work with 2 physicists, Alex Belin and Alex Maloney. With Belin. And the statement is the following. Let V be unitary CFT type VOA. And then we simply want to define our family of potentially holographic family of vertex operator algebras as the Vn being the fixed point subalgebra of the symmetric group acting on the tensor product. So basically what I described before, we take the n-fold tensor product of our underlying VOA V, and then we take the fixed point subalgebra. Then we have the following statements. First, the dimensions converge, which in particular allows us to define, at least on the level of a graded vector space, a limit of the Vn going to something which we'll call V infinity. Then the second statement is the structure constants also converge. I guess slightly more precisely, I should say, there is a way of defining the sequence of basis vectors in the Vn's such that their structure constants converge. And it's a relatively natural way of defining these sequences. So we have the structure constants converge, which allows us to define something, some numbers which we'll call f infinity ABC. So these are going to be the structure constants of the limit that we get out of these vertex operator algebras. And this limit that we get out of this family of vertex operator algebras is actually a vertex algebra. And it's defined as its underlying graded vector spaces V infinity. The structure constants are f infinity ABC, and then the vacuum is exactly what you'd expect. It's the limit of the vacuum. So this triple here defines a vertex algebra. So the statement of this theorem is basically there exists at least one family of vertex operator algebras whose large n limit can be defined and exists. I should actually say that the actual theorem is we're presenting is quite a bit more general. I basically picked out the simplest case. So let me remark something similar holds. So this large n limit exists for more general families as well. So what you can do is holds for more general. What you can try to do is you can define what is called permutation orbifolds. So what we did up here is we considered the full symmetric group Sn and took that to be our orbifold group. But of course, what you can do is you can try to find a family of permutation groups that is subgroups of Sn, and you can try to play the same game. And then potentially again, you can get a large n limit or a large central charge limit out of this. The reason I'm not really presenting this is because, not surprisingly, you have to have some conditions on those GNs. So if the GNs are, in a sense, too small, then there's not going to be a large end limit. For instance, you could, of course, simply pick GN to be the identity, simply the trivial group, the identity. And then, you would be back, Vn would simply be the tensor product. And then, of course, there would be, by the argument we gave just before, there would be no large end limit. So you need to impose an additional condition, and I really don't want to write down what that is. Let me just give you the name that we found, that we gave it. If the GN are, let's say, are what we called nested oligomorphic, then at least one holds. So at least this property that the dimensions converge. And then there's also some additional condition which ensure that property 2 holds. And actually it turns out that property 3, though, that this triple, that is essentially V infinity together with the structure constant defines a vertex algebra, is actually, it's a 3 follows from 1 and 2 essentially. So once you've established 1 and 2, then 3 follows automatically essentially. And then, so this is the result for this first problem that we try to consider. So just considering the fixed point, the fixed point subalgebra. And now you may wonder, yeah, well, what about number 2? And so, trying to obtain a holomorphic extension of the fixed point VOA. And basically this physics paper that I had with Alex Bella and Alex Maloney gives some argument that in that case the large end limit should also exist. But it's actually quite a bit harder, because essentially what you have to take care of, what you should have to worry about is now you also have to worry about, first of all, which modules you adjoin, and then the modules you adjoin, you have to make sure that the dimensions also converge. And then secondly, you also have to deal with intertwining operators. So you have to make sure that the structure constants coming from the modules and their intertwining operators also converge, etc., etc. And it's almost certainly some very similar statement as we have in this theorem here is true, but we haven't set up the proper mathematical formalism, I think, in order for it to work. But honestly, we don't expect too many surprises. So in view of time, let me maybe skip the proof of the theorem and just make one more remark about these permutation orbifolds and the symmetric orbifolds. So I mentioned initially that we started out with this conjectured example of extremal vertex operator algebras which had certain properties, and then I said part of the motivation was try to actually write down examples where we know that they exist, and these symmetric orbifold VOAs, and also to some extent the permutation orbifold VOAs do exist. But now the question is, how close do they come to this extremal vertex operator algebra? So are they very close in an appropriate sense to the extremal VOAs, or not so much? And the answer is they're actually not very close. So the question is, how close is V S infinity? So the V infinity that we got out of these symmetric orbifolds to an extremal VOA, and the answer is not very close. And to make that statement more precise, let me write down a theorem. Again, this is based on work with Alex Bella and Alex Maloney. And essentially, the theorem is simply an estimate for how the dimensions of the VNs grow in the large end limit. So if we take V to be holomorphic and of CFT type, Then what we have is the following asymptotic behavior. We have that the logarithm of the dimension of V S infinity n. So n is the weight of the homogeneous component. As n goes to infinity, asymptotically it grows something like n over log n. And I'm being very, very rough here, so there's constants in front, etc., etc. But general behavior is like linear divided by logarithm. And now if we compare that to an extremal VOA, well, basically the extremal VOA, the V infinity there, is simply going to be essentially the 1 over the eta function. That's going to be the character because we're counting Virasoro descendants. And then we all know how that grows. It grows much more slowly, so it grows like square root of n, roughly speaking. I mean, again, I'm neglecting the constants up front. And the point is simply that, n over log n grows much faster than square root of n. So in that sense, we are quite far away from these extremal VOAs. And this is some other work that Thomas and I have been doing. The idea would be if we want to get closer to these extremal VOAs, we have to find a more powerful orbifold in a sense, because the symmetric orbifold does not seem to reduce the number of states sufficiently. And so one thing you can do is we can look at families of lattice theories, because there the automorphism group that we can use is going to be a subgroup of, say, ON or OD. And potentially that's a bigger group than just simply having SN. And that's some work that Thomas and I have been doing. And actually we did find, at least for C equals 48 and 72, we found theories whose numbers are relatively close to an extremal VOA. But I guess it depends on your subjective definition of what relatively close means. Okay, then I think I'll stop here. Thank you very much.
Thank you so much. Thank you, Christoph. I'll stop the recording, and please